All right, and welcome to the final part, going through our specific heat and calorimetry section. We've done a number of calculations so far, and hopefully you've learned a little bit on how these values can be calculated, solving for different variables, or starting with moles or grams and figuring out what you need and how to solve them, keeping in mind of our units and our significant digits. So for the last section, we can kind of take a few concepts from the first two and combine them together. So if a chemical reaction causes a temperature loss, then really what we have here is we have Q, representing our temperature gain or loss, is equal to delta Hx, which is our reaction. So here we're kind of combining both MC delta T as well as that NH value, our molar enthalpy value, to figure out different types of questions. So we're going to use this example. What mass of propane, so again we've done propane now a couple of times, what mass of propane would be needed to be burned to change the temperature of 500 grams of water from 17 degrees Celsius to 95.5 degrees Celsius. So we're talking mass of propane, and it's being burned to heat up water. So we think like a gas stove, for instance. The molar enthalpy of combustion, Hc, works out to be negative 2,240 kilojoules per mole in this case. So we start this problem by saying, okay, I have energy gained and energy lost. So it's an enclosed system, and so one has to lead to the other. If something's gained, then that amount is then lost to something else. Or if something is lost, that amount is then gained. And we've been talking about system and surroundings. So what's being gained and what's being lost? Well, in this case, the energy that's being gained is the water, and the energy being lost is the propane. So that's really our first step. Energy being gained by water is energy being lost by propane. So the energy being gained by water is through a temperature change. It's going from 17 degrees up to 95.5 degrees. So that value, because it's a temperature change, is Q. The energy being lost by propane is due to it being burned off, and that's a combustion. And so that's going to be our delta H. So the energy being lost, we also have to keep in mind, is going to pick up the negative as well. So MC delta T is equal to NHC, and the amount of substance undergoing the change is our N value, and our molar enthalpy shows up here as our combustion value for N. So as we're kind of writing these out and going through, keep in mind that it's going from 17 up to 95.5. So we have our initial and our final. And we do have this kind of combustion reaction that's happening. Okay, so let's start to plug these values in and see what we end up with here. All right, so we'll move this down a little bit and just kind of see what we have here. So we can start off and we can say I've got Q water, and that's going to equal delta HC. Now we know Q water is MC water delta T, and our delta HC is our NHC value. Now this whole thing, it's being lost, so I'm going to have a negative show up here for this one. So when we start to plug in our values, keeping in mind of we have energy lost, so we have a negative, we're going to see that negative cancel out pretty quickly. So our mass value that we have is 500.0 grams. Our specific heat capacity for water, 4.18 joules per gram degrees Celsius. And our temperature change, it went from 17.0 to 95.5. So final, 95.5 minus initial, 17.0. That's going to equal negative, in this case N, what we're trying to solve for, and our HC value is 2,240 kilojoules. Remember, that's being burned off, so this value is negative 2,240 kilojoules per mole. So right away we can see our negatives are actually just going to cancel right out, right off the bat. And so for that reason, a lot of the times they don't get put in, but I will kind of add them in just to show you that the lost part should be negative, indicating our exothermic reaction, but it's being burned off, and so we have a negative value that's releasing energy anyway. So as we continue to solve through this question, we'll do the subtraction step and just kind of move our way forward. So I'm going to multiply the first two terms together, 500 times 4.18, and we're going to get 2,090. So 2,090. My grams are going to cancel, and I'm left in joules per degree Celsius. That's going to get multiplied by the 95.5 minus the 17. So that gives me 78.5 degrees Celsius equals, and then I have N, what I'm trying to solve for, multiplied by the 2,240 kilojoules per mole. So my next part now is to multiply my other two terms together. Kind of complete that step on the left-hand side. 2,090 times 78.5 gives me 164,065, and degrees Celsius are going to cancel, and that's just in joules. I'm going to have an N value, and the same 2,240 kilojoules per mole. Now, I can see pretty quickly here that I'm going to end up in joules and kilojoules when I divide this out. So it would be helpful for me if I had the same unit when I divide it over to the other side. So I'm just going to do that division. 164,065 joules is divided by 1,000. It's going to become 164.065 kilojoules. And then that's just going to equal the same value that I have on the other side. And that takes care of my units, so I know that when I divide them over to the other side that I'm going to end up with the right thing. So I have solving for my amount now. I'm going to divide each side by the 2,240 kilojoules per mole, divide by the 2,240 kilojoules per mole, and we can see that we're going to be left with moles as a unit for this. And so N is then going to equal 164 over 22, is going to equal 0.07, so 0.07324, we're just going to hang on to our digits here, 32433 moles. And keep in mind what we have here. This is the amount that's needed of propane, so C3H8. And similar to what we did before, we just need to say an amount. How many grams is that? Well, to do that part, we do a little conversion, 0.0732433 moles of C3H8 multiplied by, and then when I multiply this out, I have 1 mole on the bottom for a conversion, C3H8, and the molar mass of this thing works out to be 44.11 grams of C3H8. And so moles are going to cancel, and when I multiply the amount together here, I get 23076, just holding on to my digits, grams of C3H8. And so now I have to go through and just verify significant digits to make sure that I have, or will round to the right value. So I started off with 4 digits for water and 3 for my specific heat. Each of these went to the 10th place, which is good. That means that as I work down this left-hand side, really I have 3 digits here. This one had 4, so when I multiply this together, all of those would count, but when I multiply it by the temperature, I should only be at 3. On the right-hand side, nothing changed, 2240, so 3 digits all the way through, right to there. Even when I change joules to kilojoules, I still have 164, so it looks like I have 3 and 3, which is good. Remember, all leading zeros don't count, and then as soon as you hit a decimal, the first non-zero digit, everything after that will count. So the first non-zero digit here is 7, and then the 3, and then the 2. Those are my digits that are going to count. Okay, so basically, that's the value that will carry forward. So 732, this one has 4. Multiply a 3 significant digit number times a 4 significant digit number, I'm going to have 3 in my answer, so it should be 3.23 as a final value. Okay, so N is equal to 3.23 grams of C3H8. So helps me find the amount of that value with the right amount of significant digits. So in the last video, we'll practice one other example, and then after that will be kind of the end of this unit, the end of the first unit for thermochem. So when you're ready, we'll move on.